I'll show you a strain in space, so you can visualize it. Here is this thing that, I don't know, I hope you can see. It's not the easiest thing. I'm going to make believe the gravitational wave that you're being demonstrated is coming at you. And I'll be the agency that moves the universe here. And you'll notice an interesting thing about it. If you look at any pair of points on this thing, what is a strain? A strain is the difference in distance that two points have as a function of time divided by their initial separation. And you'll notice that in the middle of this thing, it's small, that strain. The strain is the same all over this, but the amount of motion is small in the middle. It's quite large at the edges. And that's one of the reasons now you have some image why we had to build LIGO to be so big.
Nobody really believed that you could ever detect them because the size of the effect is so small.
I came to the conclusion that, yeah, if you made this long enough.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
We have done something which is brand new.
The field has busted wide open.
It's monumental. It's like Galileo using the telescope for the first time.
I looked at it and I thought, my God, this looks like it's it.
Ladies and gentlemen, we have detected gravitational waves. We did it. I am so pleased to be able to tell you that. So these gravitational waves were produced by two colliding black holes that came together, merged to form a single black hole about 1.3 billion years ago. They were detected by LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is the most precise measuring device ever built. Let me start with what we saw. So on September 14th, 2015, the two LIGO observatories in Hanford, Washington and Livingston, Louisiana recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes in spiraling and merging together. So let me start it. All right, you can see that as the black holes spin around each other, all right, the stars behind them are warped, and that's because the strong gravitational fields bend the light that comes around. But what I want you to pay attention to in this video is the fact that as they orbit, the black holes are getting closer and closer to one another. The orbit is speeding up, and eventually they're going to merge. The event horizons are going to join, boom. So each of these black holes are about 150 kilometers in diameter, a little bit bigger than that. Take something that's 150 kilometers in diameter, so that's about a little bit bigger, maybe a lot bigger than the metropolitan Washington, D.C. area. Pack 30 times the mass of the sun in that. Accelerate it to about half the speed of light. Now take another thing, 30 times the mass of the sun, accelerate at half the speed of light and collide them together. That's what we saw here. It's mind-boggling. All right, now, let me talk about the gravitational waves. You didn't see any gravitational waves there. What you saw was actually the black holes. Now let me look at this from the gravitational wave perspective. So you're going to see, again, a computer simulation. This is a real simulation using Einstein's equations. You see the two black holes. And the green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer.